Okay, so we talked about satellite motion, and we left on kind of a weird note here, and I've changed some of this. Let me also just show you, because my explanation of satellite motion was less than optimal last time. Let me just show you. Come on. Since I have started taping things for this class, on your, I don't know if you ever go to this page or not, there's no reason to, but now there is. There's a list of available lectures / class notes, and the last two lectures that we've had, I've had on here. So if you go to the page, it goes to a notes page that's similar to what your class notes are. But if you miss things like a solution to this problem, it's got a thing you can click and you can go to that. And it'll show you the solution. It doesn't take forever. So there was a solution to that problem. But anyway, all of this is there, and you can see that the solutions are there. So come on. I had my hands in something called sodium hydroxide this morning, and it basically makes soap out of your skin. And so my fingertips are not as frictioned as they're supposed to be, and I'm having a hard time moving my my touch screen here. It's not moving as well as it should. I'm trying to make it bigger, but it's not wanting to go bigger. So let's do this. So one thing that I said that I didn't explain very well, this formula here for the velocity of, can I get one of you guys to shut that door for me? This velocity here for the formula for the velocity of a satellite, velocity equals the square root of gravitational constant times the mass of the Earth divided by the radius from the center of the Earth, is a minimum speed that you have to have in order to stay in orbit at a certain radius. Okay, and we said that this was the case, that the minimum velocity needed to maintain an orbit depends only on the radius. However, this velocity is a minimum orbit for that radius, and that's not something that was in your notes. And what's going to happen is if I have, I can't write on that. Bless you. So if I have a satellite, here's the Earth. If I have a satellite in orbit around the Earth at whatever this radius is, okay, that velocity formula, V equals the square root of G mass of the Earth over R, is for that particular radius. Okay, and what should make sense here is that the further away that I get from the Earth, okay, the further away that I get from the Earth, the less the gravitational pull, so the velocity required to keep me in orbit as I go further and further away is going to get less and less, right? And because you can see that this is inversely proportional to the velocity, that's not an R, or V, that's an R. Okay, it should make sense. The greater the radius, the less the velocity that I need to use to stay in orbit. Okay, and so we looked at what was required for a geosynchronous orbit, and I think it ended up being 3,070 meters per second. And then we looked at for an orbit that was 200 kilometers above the surface of the Earth, that this was going to be somewhere in the range of 7,000 meters per second. Okay, so it's going to require a greater velocity closer to the Earth to stay in orbit because the pull of the Earth is stronger at that point. Okay, and we try to remember in thinking about this, although it kind of hurts our brains to do that, in thinking about this, we get to a velocity ultimately. If we started at a lesser velocity, we know that the thing's just going to plummet to the Earth after a certain period of time. But basically what happens is when I get to an orbital velocity, whatever that orbital velocity is, I'm now going fast enough that I'm no longer actually getting closer to the Earth as I'm falling to the Earth. Okay? In these other cases, not only is the Earth's gravity pulling me towards the center of the Earth and creating centripetal motion, it's also causing me to speed up along that path, and therefore I get closer to the Earth. I'm not going at a velocity that's fast enough to keep me from missing the Earth. And that's basically what it is. I need to be going at a velocity that's fast enough that keeps me from missing the Earth. And at that point, at that instant, that velocity, whatever that velocity is for that radius, then I will stay in that orbit as long as I'm going that fast, as long as nothing's slowing me down. And usually we try to be above the atmosphere, so there's nothing that's actually slowing the satellite down. But the farther out I go, the less that pull of gravity, so the less the velocity that I need to stay in motion. Now, that is a little bit contradicted by something else that I said and that I actually ended up taking out of the notes, and that is that if I'm at a certain velocity and I speed up, I'm going to move into a higher orbit. Okay? So if I do speed up at that point, that doesn't mean that the velocity, or since I'm going at a greater velocity, that doesn't mean I'll go down to a lower velocity or a lower radius. That means that I could, if I wanted to, be at a lower radius, but it doesn't mean that I have to be at a lower radius when that velocity occurs. This is just the minimum velocity for me to be at, and if I want to be in a circular orbit. Okay, this is what's required for a circular orbit. If on the other hand, if I'm in a circular orbit and I'm at that velocity that is required by the radius, if I sped up, I'm more likely to increase where I go. Okay, I'm not going to go down by speeding up. I'm not going to go to a lower level of velocity. I could, but I'm not going to just by speeding up. Just by speeding up, what I said previously was that you would just go into a higher orbit, because if you increase that velocity, you're just going to push yourself further away. Okay, but as you go up, the requirement for velocity decreases. Okay, so there's that contradiction there. If I speed up, I could go into a lower orbit if I wanted to, but if I'm in circular motion here and I speed up, what's likely to happen is that I'm just going to fly further out into space. Although it's not necessary for me to be at that velocity to maintain that orbit. Now, the other thing that could happen, and this is what's more likely to happen, if I am in a circular orbit and I speed up and I stay that radius from the Earth, what's more likely to happen is that I'm going to go into an elliptical orbit. Okay? So just to be aware, if I speed up, what's really more likely to happen that I'm going into a higher circular orbit is that I'm going to go into an elliptical orbit. Okay? This tells me what velocity is required in order to be in a circular orbit, but if I exceed that velocity at that radius, I will actually extend my orbit. Okay? So at some points I will be farther away. I will go into a higher level of orbit, but I'm just going to become elliptical at that point. But that's a little bit more complicated than what the AP Physics curriculum wants to talk about. So I just wanted to make that clear. I wasn't very clear when I discussed that or described that last time. And you may recall that I said something just doesn't seem right to me here when I did this problem. And we did actually complete this problem. I'm not sure why the writing moved, but actually the text moved. But anyway, we did complete this problem, and the answers that we got were correct. So I'm not going to worry about it anymore. And that's on the Canvas page as well. Okay. So anyway, I don't want to belabor that anymore. Hopefully that makes sense. Another topic that we talk about related to circular motion is weightlessness. And there's a difference between true weightlessness and apparent weightlessness. Apparent weightlessness is a phenomenon experienced when an object is falling towards a gravitational body at the same rate as your frame of reference. Okay, so if I'm on the International Space Station, I know that the International Space Station is in orbit above the Earth, but it's still close enough to the Earth to be under the Earth's gravitational influence. This always used to bother me. It's like, well, they look like they're weightless, but you're saying there's gravity up there. And in fact, there's significant gravity up there. It's not 9.8 meters per second, or per second squared, but it's still significant gravity. And the International Space Station is falling towards the Earth. Okay, and remember, the way that we explained that was International Space Station wants to go straight, but gravity is pulling it into a circular orbit. So International Space Station wants to be here, but gravity has accelerated it that far towards the center of the Earth. Okay, so gravity really is pulling it towards the center of the Earth. But I'm also on the space station, and I'm under the same influence of gravity that the space station is. So I'm going to be falling towards the Earth at the same rate that the space station is. So in that circumstance, relative to my frame of reference, I can't tell that I'm falling towards the center of the Earth, can I? Okay? but I can't tell that the space station's falling towards the center of the Earth either. Nevertheless, it is, but we're both falling at the same rate. So I appear or I feel weightless because my frame of reference and and myself were falling at the same rate. So in this frame of reference, objects don't appear to fall. Nevertheless, gravity is acting on them as well as on the frame of reference. Spaceship in orbit is an example. Both are pulled towards out of their straight line path of motion into a circular path by the force due to gravity. So that's apparent weightlessness. What have people tried to do to sort of mimic this and give everyday people an opportunity to experience this? Yeah. Yeah, the vomit comet, right? The planes go up to a high altitude and then they just free fall straight down. Okay, they shut off their engines, they free fall straight down, and you're both falling at the same rate. And you can't tell that you're falling, okay, because your frame of reference is falling at the same rate you are. You don't know that you're falling. You appear, you feel like you're just hanging weightless in space. Okay? And that's all that is, that apparent weightlessness. And it makes a lot of people sick, so they call it the vomit comet. Okay? So, on the other hand, if you're in an object and you're nowhere near a gravitational body, you would experience true weightlessness. There wouldn't be any difference in that feeling. Okay, you would true weightlessness versus apparent weightlessness would feel the same. Okay, any questions about weightlessness? Okay, so the last part of this relates to some additional mathematical laws that we figured out along the way. And again, these are empirical laws. They're just mathematical laws that explain what we see. They don't explain why it happens. Newton came along and did that a little bit later, but they explain what it is that we're actually seeing. And we are aware that we have this sort of history of our philosophy about where we exist in space. And in the 2nd century BC, Ptolemy had this geocentric view, meaning what? Yeah. Yeah, the Earth is the center of our universe. And then in the 1600s, Copernicus and Galileo came along, 1500s, 1600s, and they figured out, hey, we revolve around the sun, not the other way around. And then also in the early 1600s, Kepler, or Brahe, was more at the end of the 1500s. He died in 1601. And then Kepler was the early 1600s. He died in 1630. Anybody know what Brahe's first name is? No? This is Tycho Brahe.
That's a fun name.
And you may be aware that if you look up at the moon and that huge crater at the bottom of the moon that you always see, that's named after Tycho. That's crater Tycho. So Tycho Brahe, it's named after him. But Kepler, both of these guys were just phenomenal data takers. They believed in you have to do everything to the exact gazillionth of a decimal point, okay? And they kept very, very, very specific data on planetary motion. And they were able, without computers or without tremendously high-powered telescopes, to be able to figure out some empirical laws just by observing the paths of the planets. They found out three things. Well, these are Kepler's laws. Kepler was a student of Brahe, and he continued his work after Brahe died. But the path of each planet around the sun is an ellipse with the sun at one focus. Okay, and I'm sure you've heard that our orbits are elliptical and the sun is at one focus. It's not quite that bad. It's more, it's a little bit more like this. Okay, so it's not hugely elliptical except for a couple of the outer planets, but that would suggest to you that the velocity of the planet is greater than the velocity that's required of it to be in circular motion, right? To be in circular motion, we know that the velocity of a satellite needs to be gravitational constant times the mass, and in this case it would be the mass of the sun divided by the radius. So the velocity of the planets are actually a little bit greater than this because we've got this elliptical orbit. That's not going to make any difference to us, but it's a conceptual thing that's something that's helpful. Okay, the next thing that they found out was that each planet moves so that an imaginary line extending from the sun to the planet sweeps out an equal area in equal time intervals. So if I am the Earth, and I draw an imaginary line to the Earth here, and I say a month passed between here and here, okay? If I go somewhere else in the orbit and a month passed, the area of this segment has to be the same as the area of this segment. Okay, so the area of this has to be the same as the area of this. And in fact, I might even need to make that a little bit less, huh? So let's make it like that. Okay, what happens as the sun gets closer to or as the Earth gets closer to the sun in its orbit?
The days get longer.
Huh?
I said the days get longer.
Okay. Actually, that's not true. The sun is further away from the Earth is further away from the sun in the summer than it is in the wintertime. It's just the angle, right? But what happens is as I go around here, if I go from here to here in 1 month and I go from here to here in 1 month, what do I know about the velocity here compared to here?
It's slower when it's closer to the sun.
It's slower when it's closer to the sun. I'm going a lot farther in a month than I am here.
Oh,
It's going faster. And why would that make sense? Because
you said so.
the gravity of the sun's stronger there, right? The gravity of the sun's going to be stronger here than when I'm way out here. Okay, so as I'm closer to the sun, I'm going to sweep out, and that's what this is called. This line sweeps out this area, and it sweeps out this area. For the same time period, it sweeps out the same area. Okay, now that's not something that we actually use. We just observe that. The third thing that they figured out was that the ratio of the square of the periods of any two planets, okay, the period of planet 1 to planet 2, okay, is equal to the cube of the ratio of the mean distance from the sun. And we have to use the mean distance here, okay, because these are elliptical orbits, so we say that it's the average distance from the sun. But again, the ratio of the period squared is equal to the ratio of the average distance cubed. Or we could say that the distance cubed divided by the period squared of one planet is equal to the distance cubed divided by the period of the other planet. Okay, and this is mind-boggling, not only because it's a difficult concept in general, but it's mind-boggling. What does it mean for this ratio of any planet? the ratio of its distance to the sun versus its orbital period. What does that mean for any planet? Has to be what? So if this was Mars, let's say the orbital distance to Mars divided by its period equaled the orbital distance of the Earth divided by its period squared. What's that say about this ratio for any planet of our solar system? It has to be what? It's got to be constant. What the heck? This value has to be constant. Okay? And that should just kind of blow your mind. Why would we expect the distance of the planet from the sun divided by its period to be a constant value for each planet? It's the same for every planet in our solar system. That ratio is the same for every planet in our solar system. We're going to see why that is in a little bit. Mars' period was noted by Kepler to be about 687 days, which is 1.88 Earth years. Determine the mean distance of Mars from the sun using the Earth as a reference. The Earth's distance to the sun is going to be 149.6 times 10 to the 6 kilometers. Okay, and I've asked, do we actually have to plug all the numbers in seconds and meters in this case? We're always beating that drum, put everything in meters and seconds. But these are ratios, okay? The s cubed over t squared, that's just a ratio. So as long as I use the same units for everything, I'm going to be fine. I don't have to do that, okay? So we want to know how far Mars is from the sun. And so we can say the distance, and that's going to be the letter S in this case. The distance of Mars from the sun cubed divided by the square of its period is going to be equal to the distance of the Earth from the sun divided by the Earth's period squared. And the nice thing about this again is we're using ratios, so I can just use Earth years to calculate this. Okay, I can just say my period for the Earth is 1. Okay, so we're going to say the distance of Mars from the sun cubed equals the square of its period times the cube of the Earth's distance divided by the Earth's distance, or the Earth's period. And so that's going to equal 1.88 squared times 149.6 times 10 to the 6th kilometers divided by 1 squared. Remember, this has to be cubed. Okay, so that 1 just kind of drops out, doesn't it? And then we have to do what to the whole thing?
Cube root.
I have to take the cube root. I don't have my calculator with me. And what do we I'm sure I've asked this before. What do we normally do when we want to take something other than a square root? The easiest way to do that is just raise it to the 1 over that power.
Yeah.
So we would raise it to the 1/3 power. It's a lot easier to do that than what you have to do on a calculator to get the cube root. Let's see if I can make my calculator do this.
Yeah, it's something like
I'm not going to be using that calculator is too complicated. Got an answer?
that. Yeah.
Yeah.
How many kilometers?
Hold on. 227,870,574 kilometers.
So 2.27 times 10 to the 8th kilometers. And you said 227, didn't you?
Yeah.
Yeah.
Okay, so 2.27, 2.22. Okay, somebody Google what the distance from the sun to Mars is. Yeah, Josh.
What's on the, like it said the cube root, what's on the bottom after the,
Oh, that's just a 1 squared crossed out,
okay.
since it's just 1.
It is 228 million kilometers away.
Okay? So that's pretty accurate, huh?
Yep.
Okay, you said 227, how many thousand? Would it round up to 228?
Yeah.
Okay, so sorry, it rounds up to 228, huh?
Yeah.
Okay. So these guys did this in the 1600s without any kind of calculators or anything like that. Just their observation said, hey, you know what? If I take this cube of the, this distance and divide it by the square of its, I mean, how do you come up with something like that? The observational genius of those individuals had to be amazing. Now, that's the way science kind of works. I make observations, then I describe it using mathematics. This is how mathematically I can characterize this, but still doesn't say why it works, does it? Doesn't say why it works. And it wasn't until Newton came along that we really understood why this happens. So, although orbits are elliptical, they're usually circular enough that we can treat them as circular, and this makes the mean distance the radius of a circle r. We also ignore the masses of other planets on each other in our work. So let's look at Newton's second law for centripetal force and the universal law of gravitation. Remember, we said that when we have something traveling in a circular motion, we can equate mv squared over r to whatever force is causing mv squared over r, right? Because this is just saying this is the centripetal force, right? Mass times acceleration. That's the centripetal force. Well, what's causing the centripetal force? And in this case, it's g m1 m2 over r squared. Okay? Since it's gravity, we can equate this force with the formula due to gravity. And we can do that with anything. If I want to find out what the the force. So for example, when we talked about the banking of a curve, right? If we had a banked curve, we had to find out what the normal force, the x component of the normal force was, and we equated that to mv squared over r. Okay, and that gave us a banking formula. Anyway, so we remember that one of these masses is the mass of something that's pulling, and the other is the mass of the thing that's being pulled on. This is the mass of the thing that's being pulled on. Okay, so that's going to cancel out with the mass of the thing that's being pulled on over here. And we're probably going to say that this is the mass of the sun. So let's say that the thing that's doing the pulling is the mass of the sun. So and so the radius of, or the orbital radius, I don't know why I needed to put R1 there. So, well, it's going to be the radius of the orbiting thing. But I can cross that out, right? Because I've got two of those. Let's not do that yet, because that's going to cause problems. So let's not do that yet. Let's say v squared over r equals g mass of the sun over r squared. Okay, now I don't know what v1 is. How do, when I have a centripetal motion problem, how do I resolve the fact that I don't have the velocity? What do I convert that to?
Acceleration.
V squared is the same thing as 4 pi squared over r times the period. Right? Okay. So that's why I didn't want to cross this r out, because I'm going to do that here. Okay, so now I know that v squared over r is the same thing as 4 pi squared r over t, and now I'm going to equate that to g mass of the sun over r squared. And now what's going to happen to, let's see, what do we want to find? Oh, I'm going to want to, and that's the period squared actually. Okay, so now let's put this over here. Right, we can multiply both sides of the equation by r cubed, and we can take, or by r squared, and we can take this and put it down here, and we're going to get the radius, or the orbital radius cubed over t squared equals gravitational constant times the mass of the sun divided by 4 pi squared. Okay, what type of a value is that? Does it ever change? It's a constant, right? Check that out. The distance to the planet cubed divided by the square of the periods is a constant. And the only thing that constant depends on is what the mass of the sun is. So for our sun, this value will be the same value for any planet. For some sun in another solar system, it's going to depend on what the mass of that sun is, but we could still use it to figure out what this ratio is. And once I know what one thing is, one planet is, right, I can figure out all of the other planets' ratios too by just knowing how far away from the sun, or what their period is. So if I observe their period, I can find out that their orbital distance from the sun is a certain amount. Okay, and they figured all this stuff out in the 1600s. It's just unbelievable. Okay, but anyway, gravity, the universal law of gravitation, explains why this ratio works. Okay, so we made the observations, we created this law, and then Newton came along and said, well, this is why this law works. And that's kind of the progression of science. Okay, so this is Kepler's third law for a single orbiting body. Using the same analysis for a second planet, recognizing that the ratio of r cubed to period squared has to equal the same as that for the first planet, we get the complete version of Kepler's third law. So this is just Kepler's third law for a single orbiting body. Okay, but if I recognize this ratio has to be the same for all planets, then I can say, well, r cubed of Mars versus its period squared is the same as r cubed Earth versus its period squared. Okay, and then we can do some cool things like figuring out what the mass of the sun is. So determine the mass of the sun given the Earth's distance from the sun as 1.5 times 10 to the 11th meters. Was that what we said it was before? We were a little more specific before, weren't we? We said 1446.9, something like that. Okay, so all we have to do is rearrange our formula to figure out what the mass is. And that becomes 4 pi squared times 1.5 times 10 to the 11th meters cubed over. Okay, now here's the question. We're not dealing with a ratio anymore. We're dealing with a single value. We're going to need to turn this into seconds. So 365 days times 24 hours times 60 minutes times 60 seconds, and all of that has to be squared. And then that's got to be multiplied times 6.67 times 10 to the negative 11th, which is our gravitational constant. And so you guys are going to do that. I'm going to see if I can kind of figure out. So 10 to the 11th cubed is 33, 34, 35, let's say 36. So 10 to the 36 on top, about. And then 10 to the second. 10 to the 13. Square. 12. So somewhere in the range of 10 to the 35th kilograms?
On 10 to the 30th.
30th, okay. What times 10 to the 30th?
2.01. Let's round it out.
times 10 to the 30th kilograms. Okay, so somebody Google it and see what it is. Remembering that the Earth is 5.98 times 10 to the 24th kilograms.
1.9891 times 10 to the 30th.
Okay, pretty dang close, huh? Okay, look how much bigger the sun is than the Earth. It's like 1,000,000 times bigger than the Earth. And you start to I mean, it starts to actually become real rather than just this kind of abstract thing. When you start working with these numbers, first of all, you figure out, man, I can make a lot of mistakes if I'm not careful with how I put this into my calculator. I can forget so many of these cubes and these squares, but it really makes things a little bit more interesting related to astronomy. But again, to figure all this stuff out in the 1600s just, had to be a pretty exciting time to be a scientist, because all of this stuff was just brand new. We can't totally ignore gravitational pulls by other planets. They do cause deviations from predictions of Kepler's laws. We call these deviations perturbations. Perturbation in the orbit of outer planets were clues that led to the discovery of planets further out. It was also a perturbation in the motion of Saturn that allowed Newton to conclude that the law of gravitation was universal. Okay, and even that's just an amazing thing to think about. And we have even seen these laws in action in other planetary systems. We've been able to, look into outer space to the point now where we've seen enough solar systems and other star systems that we can actually see these laws in action in other planetary systems. Kepler's third law can also be used for other systems like moons and satellites orbiting the Earth. Because Newton pulled from the work of others in developing the laws of motion and laws of universal gravitation, we often call Newton's entire body of work related to motion Newton's synthesis. Okay, we don't need to do this. And that's pretty much it. We'll talk more about this kind of thing later on. That's just something. So we need to have some kind of an assessment. I can tell you right now that whatever that is, it's going to be a take-home assessment. It's not going to be an in-class test. We don't really have time to use a class period for a test at this point. And so we actually need to start worrying about the next topic, which is going to be work. Not work in the way that you think of it, but work in a way that's going to be very confusing. Okay. I don't want to, I thought it was going to take me a little bit longer to get through the rest of this. Actually, let's see if I can find some problems that we can do. Just a second.
don't know why I didn't put any problems in the packet. Some dead air time on the video. Okay. Oh, I was looking for multiple choice questions.
Okay. Person stands on a merry-go-round which is rotating at a constant angular speed. Which of the following are true about the frictional force exerted on the person by the merry-go-round? Select two answers. Okay, the frictional force on a person by the merry-go-round. Force is greater in magnitude than the frictional force exerted. By the way, what's causing the centripetal force in this case? The person standing on the merry-go-round and he's not holding on to anything. He's just standing on the merry-go-round as it goes around. What's causing the centripetal force?
The movement of the friction of the person against the moving of the merry-go-round.
Okay, so the force of friction between the merry-go-round and the person is what's causing the person to be pulled into a circle, right? Okay, that's a little bit weird, just even thinking about that. But if the force is greater in magnitude than the frictional force exerted by the person on the merry-go-round, what's wrong with that? If the merry-go-round's exerting a force of friction on me, and I'm exerting a force of friction on the merry-go-round, what do I know about those two forces? They have to be what? They have to be equal, don't they? Right? Because of Newton's third law. So that can't be great. That can't be true. Okay? Force is opposite in the direction to the frictional force exerted on the merry-go-round by the person. That's always going to be the case with action-reaction forces, right? They're going to be in opposite directions. So that's true. The force is directed away from the center of the merry-go-round. That's not true, right? Because it would have to be directed towards the center of the merry-go-round, right? And then the force is dependent on the person's mass. Okay? Force equals mv squared over r, right? So whatever that frictional force is, and we could calculate it. We could set mv squared over r equal to mu fg. So is it dependent on the person's mass? The specific force is dependent on the person's mass, isn't it? Okay, so, but if I wanted to solve problems, I wouldn't have to think about that. The force is dependent on the person's mass, though. So whatever that force is, the heavier person, the force exerted on that person by the merry-go-round would be greater, wouldn't it? In order to pull a heavier person or a more massive person into a circular motion, would require a greater force. Right? Ball is attached to a string, whirled around in a horizontal circle having radius r. We did that. If the radius of the circle is changed to 4r and the same centripetal force is applied by the string, the new speed of the ball will be which of the following? Okay, my advice to you is never to try and logic one of these out, but to actually write out the formula. You know that, oops, can I not write on that? Oh, I can't. No, I can't write on that. Okay. I don't think I can. Okay, so I can't write on that. But I'm I'm always going to write out the force, or I'm going to write out the equation. Centripetal force equals mv squared over r. And what is it that I'm trying to find? The velocity. I'm trying to figure out what's going to happen to the velocity. And so I can say v squared equals fc r over m, right? Or I can say that v is equal to the square root of that. And what is it that I'm doing to the radius? So I'm multiplying this by 4. Under the square root, what effect is that going to have on the velocity? It's going to multiply the velocity by 2. Okay? So don't even think about trying to logic something like that out. Just write the formula down, say, well, what is it that I'm changing? And then what effect does that have on the variable that I want? I'm sure most of you could have, if not all of you, could have come to the right conclusion by logicking it out, but it's just faster not to. Racing cars moving around the circular track of radius 300 meters is shown above. At the instant when the car's velocity is directed due east, so I would come and I would write an arrow on that. I'm not going to be able to here, but at the instant when the car's velocity is directed due east, its acceleration is directed due south and has a magnitude of 3 meters per second squared. When viewed from above, the car is moving. First of all, is it moving clockwise or counterclockwise? Its motion is directed due east. And that's the only point there on the circle right at the top that I'm going to be able to see that. It's not directed due east anywhere else on that circle. Well, what if it was going the other way though?
But then it would be accelerating north.
Okay, so that's the other question, right? If the acceleration is directed due south, it has to be directed towards the center of the circle, right? So, okay, so you guys seem to have a fairly good intuition for this. Is it going to be 30 meters per second or 10 meters per second? And how am I going to figure that out? What's causing my centripetal acceleration here?
Friction.
That's not going to be very helpful, is it? So, what else, other information were we given? How am I going to figure out how fast it's going? Or what its acceleration is?
You plug in the 4 pi squared r over t.
To what? How's that going to help me?
You have to
Do
Do I need to do that? I forgot that we had acceleration, so. A equals what, V squared over R? Okay, so V equals the square root of RA equals the square root of 300 meters times 3 meters per second. Okay, and that's 3 meters per second squared, isn't it? So notice my units here are going to be meters squared per second squared, but the square root of 90 is what? Or 900 is? 30 meters per second. Okay, so it took me a minute to think about what it shouldn't have, but and all they're really wanting you to be able to do there is equate centripetal acceleration with V squared over R. Okay, horizontal turntable shown above rotates at a constant rate. As viewed from above, a coin on the turntable moves counterclockwise in a circle shown. Which of the following vectors best represents the direction of the frictional force exerted on the coin by the turntable when the coin is in the position shown? See?
Went to the center, yeah.
Okay. So
Is the thing above the
that's just showing the direction of the rotation. So C is the correct choice because the force on the coin is in the downward direction, right? Okay. The coin is not accelerating in the tangential way, right? It's not accelerating around the circle, so there is no tangential force or tangential acceleration on it. It's all directed towards the center. Okay, there might be a desire in this case to pick B because, well, isn't friction also moving it towards to the left? But it's not accelerating around the path, so the forces on the nickel in that direction are stable. Okay, there must be a force in the backwards direction too. So anyway, C would be the correct answer. I'll print off the packet for this, and what I'll probably do is, as an assessment, just assign you some homework problems from the packet. See if you could work through those. And I think I might have an answer key for most of those, so but it may not be next time that we do that. So Easton, I'm just going to give you the test. And I'm just going to ask ask you to take it home.
Okay, I couldn't, sorry, the link that you gave me, it just took me to like the Microsoft website. It didn't actually take me to the,
Okay, did I give you a link?
it like, I think you did, maybe you didn't actually.
Okay, because I don't recall actually giving you a link. I know I gave one to, I just emailed the test to Josh, and it's no big deal. Just take your time, try not to use
I
sources.
won't use notes on it,
So
there's
just-
no point.
Yeah,
I won't
so,
learn anything.
so go ahead and if you're struggling with any of those concepts, just ask me
Okay,
for help.
I would stay after school, but I have work and
Don't
stuff.
worry about that. Just take it home and do it at
Alright,
home.
thank you.
Take care.
You too.